Welcome to a little overview of ontological databases. It shows the difference between traditional database engines and so-called ontological databases. Now, what are those two types of database good for? Traditional databases, they process a lot of well-structured data in a very consistent and fast manner. Ontological databases, they allow the loose definition of relationships. It supports the organization of incomplete data. It allows for simple mapping of natural context, so-called real-world mapping. And it's an easy expansion, automatic integration into graphical user interfaces when they are kept generic. Traditional databases. They're based on the relationship model invented in the early 70s, and they are based on fixed dependencies between entities. For example, a person has one or more addresses, a person has one or more bank accounts, and that bank account has one or more account entries, withdrawals, deposits, etc. That is good for processing large data that are well defined. But what if those structures will change? New relations are being added and unforeseen data structure will get there too. For example, when there's a new entity of contract or contract parties or communications, then programmers would have to be deployed to implement those changes, and that costs time and money. Now, the normal life cycle of IT applications is you do requirement analysis, you do design, you do an implementation, you test it, both parts technically and by the user, and then the application goes into its evolution and the whole thing starts anew. Because the evolution is simply the operation of the application until someone says, hey, we need to have something more, and then the requirement analysis starts again. Depending on the type of application, that can take months to years, also depends on the experience of the programming team. The expected benefits of the ontological approach is 0% when it comes to requirements, because you still need to know what you want to do. When it comes to the design, you may probably save 80% of the effort, because the subject matter experts, meaning your users, they already know what they need and what is necessary in order to make their life better or to implement a new functionality. When it comes to the implementation, you save even more, because during the design process, you are already implementing the changes. The test phase still needs to be executed, and you do not save that much. And of course, you do not save anything during the evolution. An ontological database consists of a few basic components: classes, attributes, and relations. Every person has a first name, a last name, probably an eye color. A vehicle has a manufacturer, it's a model, it's built in a specific year, and animals have that too. The classes and the attributions, they define the what. Now when it comes to the relations, they are being defined in the form of the subject, predicate, and object. A person likes another person. A person is the daughter of yet another person. A person possesses a vehicle, etc., etc. And when relations need attributes, they can also be added. For example, you got married at a certain point in time, you might get divorced at a certain point in time. In a real-world example, it can look like this. Paul, for example, is the husband of Leah. Leah is a friend of Shireen. Shireen is the CEO of Fin Advice Corporation. Barry is the godfather of Lisa. Greg apparently is the father of Lisa. Lisa is an employee of Financial Advice Corporation. Barry is also convicted of fraud. That's a property that not many people have, a few do. And is also an employee of the Financial Advice Corporation. He might not be that because apparently he has been convicted of fraud. In theory, it looks like this. The model consists out of classes, attributes, and relations. As I said earlier, a very few basic components. When it comes to storing data, the instance of a person consists out of attributes, consists out of relations, consists of another person, is employed by some company or likes something. Same with contracts. Greg and Paul are the contract partners, and there's a contract text to it. Machines have yet other properties, are stored in a different way, as they do not have systems, they are not employed by something or someone. Now here are the pros, the cons, and the in-betweens. All objects can be modeled without a programmer. Relationships can be created between all types of classes, so there's no fixed definition of relationship between one class and the other. Everything is being made by definition that you, the modeler, puts into place. For example, a person can be a sister or a brother of someone else. The person cannot be owned by someone. A pet can be owned by a person. Same thing as a machine cannot own a pet. So all those definitions that are very soft and very humanly defined must be done by the modeler. It is a perfect source for AI and machine learning programs because relationships can also be inferred between classes. So not only the fixed definition of relationships between, for example, a person and another person, but also the inferred relationships between a person over another person can be defined or can be found out. For example, a person can be the grandfather of another person, even if that is not being fixed defined by the modeler. Basic engine can be used for all kinds of application. Yes, you can also create banking applications with that, but for those applications, the traditional database model might be the more preferable. The automatic generation of data warehouses is fairly simple because the relationships between those classes are known and can be very easily being transferred into data warehouse tables or views. Now, the in-betweens. The creator, they must have subject matter expertise because you still need to know what you want to do. The user interface is universal because all the information that the user interface needs are contained within the system tables of an ontological database. The latter is automatically also then a con because the user interface will pretty much always look the same because it's generic, but you do not need to spend any time on creating that. When it comes to the architecture, here's a high-level overview of the architecture, how it can operate. User interface communicates with an API. That API sends all insert, update, and delete operations to the operational part of the database. An ETL process then pushes the data into a data warehouse, and all selects are being made on that data warehouse, thus taking load away from the operational part. In a cluster situation, it looks nearly the same way because user interface again communicates with the API. All data changing operations are being sent to the primary node. All reading operations are being sent to the secondary nodes. When it comes to a cluster-aware situation with the data warehouse, this can even be horizontalized in a broader way. The user interface again goes to the API. All changing operations are being sent to the primary node, which are then being replicated automatically to all the secondary nodes where the reads can be executed, and all analysis can then run on the data warehouse, making it even much more scalable than before. When it comes to use cases, non-linear applications are predestined to be used in ontological databases. For example, journalistic research systems, customer behavior analysis, but also traditional processing systems like order systems or construction systems are really well versed to use this. It's always the same engine, but different models on that engine. For example, research models can be realized by that. Construction systems that need a lot of components can be implemented like that. Logistical models can be implemented as well as criminal investigations, where a lot of relationships between facts, cases, suspects, etc. must be established.